Well, today I wanted to talk about Onium modeling all mesons and baryons. And what's special today is I recently published two papers, one on all the mesons and one on all the baryons. And by all, I mean all the ones for which there's substantial data on the mass and decay products, so I have something to work with. And that was 220 mesons and 176 baryons listed in those two papers. And I'll put the two papers up briefly so you can see the titles. And I'll put the links below. Now, this was a project I started 6 years ago. And the idea behind the project is if it was possible, to find if it was possible to model all the mesons and baryons using only electrons and positrons for the mesons, and with the baryons using electrons, positrons, and protons, any protons, or neutrons, or any neutrons, for modeling the baryons, and which basically eliminates the need for the quark theory. And in order to do that, I decided to try it with the Onium model, the relativistic Onium model that was first published by Sternglass. Now, the model was actually first published in a book by Milne, but most people didn't see it. So Sternglass is recognized as the first publisher of it in a scientific journal. Now, Richard Feynman was the one who suggested to Sternglass that he model the relativistic electron-positron pair. And so I give Feynman credit for the suggestion, even though Feynman chose not to be a co-author on the paper, which is something that I find regrettable because the entire particle theory world would be vastly different if Feynman had put his name to this theory back in 1961, before quark theory had taken hold. But the basic idea with Onium theory is positronium is electron and positron that are orbiting. They're pulled together by the Coulomb attraction, because they're positive and negative charge, but if they spin rapidly enough, there's a centrifugal force pulling them apart. And when those two forces are equal, then you get positronium. Well, what Sternglass worked on was a relativistic solution. What if there's a second solution at a relativistic rotational velocity that's at a smaller radius? And he found that there was. And there's another derivation by Peter Brown that was published in Nature in 1966 that is a cleaner derivation, and it's the one I recommend people read if you want to prove to yourself that this is a real thing. But what Sternglass realized, and Feynman realized, is that the solution was 140 MeV, so it was the neutral pion. So it was a classical derivation of neutral pion. And basically, the mass works out to 2 times the mass of the electron, because you have both an electron and positron, divided by the fine structure constant. And 137 times 0.511 equals approximately 70 MeV per c squared, and 2 times that is approximately 140. Now, Sternglass realized that if you have this pion orbiting an electron, then you can get either a muon or a pion mass, depending on the direction of the orbit. And then Brown came up with a model, well, what if you put the actual electron in the middle, and then you have 2 electrons orbiting it? That also gives the muon mass. So that was 2 different basic types of models. However, Brown also realized that you could have a positive charge orbited by 2 negative charges, or you could have a positive charge, say, orbited by a positive and negative charge, like in the positronium state. So there's really 3 different models, and that may be why we see different angular momenta from different types of muons. And I plan to do some calculations to see if these models match up with the muon problem, but that's a problem for a different day. Now, if you have a proton orbiting an antiproton, the energy of that essentially the proton times the fine structure constant, is 124.86 GeV, which is really close to the first measured energy, mass energy of 125.18 GeV per c squared. So that is essentially explains the Higgs data bump. And then you can have a relativistic protonium that has about twice that energy, about 247.84 GeV. And so that's something that we should see in the future if we haven't seen it already at CERN. Now, as I said, I modeled 220 mesons. 170 of those were within 5 MeV accuracy for the mass modeling using this relativistic model. And then 164 baryons, and I got 0.2% relative error of 111 out of the 121 DB, charmonium, and bottomonium mesons. And then I also got 74 out of 76 within 0.2% relative error for all the charmed and bottom baryons. So it's possible using this model to get very accurate analysis. Many of these were within 1 MeV. And you have cases where you have co-located resonances. I prefer to call them resonances rather than particles, because that's what they are. They can be co-located, they can be in this trionium orbit, as Brown referred to it, and they can be stacked, so you can have multiple resonances on top of each other with slightly different orbits because they're different energy. Actually, the more energetic orbit, the particles, the smaller the orbit. So it's possible using all those things to come up with these models. And in my papers, I give like brief graphical descriptions, and I also give the calculations. And I'll also put in links for the Excel spreadsheets I use to do all these calculations. So if you want, you can play with it and come up with alternative models if you prefer using different compositions. But the way it works, in a really great example, is the rho-meson. The rho-meson has a mass of 775 MeV. In some of its decay modes, they decay to 4 pions. So I say it's a 4 pion element or resonance rather than a single pion resonance as it is in the quark theory, because that matches the decay products. And one of the strengths of my model is I match it up with the actual decay products as being the actual physical composition, while in quark theory the decay products appear by magic or some unknown source. So if the rho contains 4 pions, its mass happens to equal 2 pions plus a kaon. And a kaon equals 2 pions. So that's where you get your 4 pions. If you sum the mass of 2 pions and a kaon, you get 776 MeV per c squared, which you can compare to the measured value of 775. And so that's basically how this model works. And in the tables in my papers, I list the composition of every single one of these resonances. And then in a spreadsheet, I make it clear what the relativistic mass is due to the orbital energy. So the strengths and advantages of this is, one, you do away with quarks. You just need electrons and protons, and maybe occasionally neutrons. In general, with onium theory, you need charged particles because they're interacting using electric charge. So while there are some resonances that look like they have a neutral particle in them, it's generally going to be charged particles that are interacting. And then the mass is relativistic beyond the rest mass of the electron and proton. So that explains the mass. And in the current theory of quark theory, the mass is, once again, magic. There's no theory for how the mass of certain particles is what it is. Then you have the k short and k long, which is a really important example. We have kaons, neutral kaons, that both have the same energy, but have different half-lives. And there's no good explanation how that is in the quark model. And at the same time, the neutral kaon can decay like it's matter or antimatter. So, and this is true of many particles that are heavier than the kaon, that they have matter and antimatter versions, even though they're neutral, which would indicate they have the same number of oppositely charged particles. In the case of a kaon, 3 electrons and 3 positrons. So it's electrically neutral. And it should be matter neutral too. 3 matter particles, 3 antimatter particles. So it can't be matter antimatter. So what's going on? Well, what's going on, if you look at the K naught, there's 2 types of K longs, and they decay to a muon and a pion, so that's what they are, a muon and a pion, predominantly, is what they predominantly decay to, so that's what they are. But it can be a negative muon or a positive muon. And if it's a negative muon, it'll preferentially decay with an electron in a decay. If it's a positive muon, it'll decay with a positron in a decay. That's where you get matter and antimatter decay streams. And this is true for all the heavier particles where there's a muon as part of the particle where its orbit, it affects how its decay modes work. And you can see this in the decay modes of charged particles as well. Now, the K short normally decays to 2 pions, and that's what it is. And the reason we have this problem with the decay modes is if you take a pion and a muon, as I said, they orbit in opposite directions. But when they couple, they're orbited the other way. So a muon and pion orbit together, which allows them to last longer, while a pion and a pion orbit in opposite directions, which causes them to be less stable. So the solution to these 2 problems is just simply built into the Onium theory, while they're unsolved problems within the quark theory. Now there's also rule breaking modes, and as I discussed, you can have electron orbited by oppositely charged particles in an Onium orbit, or you can have electron orbited by 2 particles that are the same charge but opposite to the central particle or groups of particles. And so this gives you 2 different configurations that have the same mass, but they have different decay modes. And what we find is this version where you have 2 light charged particles in orbit around the opposite charge generally have the rule breaking decay modes, the ones that you wouldn't predict based on the rules that are based on the other type of Onium orbit where opposite charges are in an Onium orbit. So that's where the rule breaking comes from. To be clear, nature does not break any rules. It's our rules that are wrong if nature breaks them. So if you have a theory that has rule-breaking decay modes, then your theory's wrong. And you need a new theory. And so Onium theory is another new one. Now I can go on there because there's dozens of reasons why quark theory is impossible. It can't describe a proton, even less anything else. And when you talk about mesons, you're talking about 10 different quarks, not counting the top, because the top isn't actually part of any particle. You have 10 with 5 being matter, 5 being antimatter, in groups of 2 that are supposed to form 220 mesons plus. There's actually over 250 that have been observed, with some of them not observed well enough to have enough data for me to do anything with them. So you can't get 250 plus mesons from combinations of pairs of 10 different particles. It's impossible. So I could have listed that as another lead letter here. But basically, quarks are not needed. So that simplifies the whole particle model. And I could also add in here that under Onium theory, the muons, as I've shown here, are not elementary particles. and neither are tauons, which also simplifies particle theory. So the Onium model overall is a much better simplification of particle theory. And I consider my quest to see if there's a model where I could use just electrons and protons to model all the unstable resonances, I consider it to be a really great success. Now, are there problems with it? Of course. Does it need work? Of course. This is just a basic outline of a solution. And I outlined it in my book, Goodbye Quarks, the Onium Theory, which is for sale on Amazon. But as a follow-up to the book, I needed to model everything. I needed to make sure there wasn't any particle that I couldn't model. And that includes the WZ, Higgs, and TOPS, the heavier ones that have a relativistic proton. And note I use relativistic mass in a general sense. I can do an entirely different video on what I mean by relativistic mass. But not to get distracted, this is basically what I've done. I've shown that it's possible you can come up with a much better overall particle theory, and we should. It tells us that we need to start over with particle theory with something more basic because it's possible, it's doable. And this is, it may be that someone can come up with a better solution than what I have, but someone needs to come up with a solution because we can do better than quark theory. So I hope you enjoyed this, and thanks for watching. I hope if you are so inclined, you pull up a copy of my paper and try to read through it. It's more technical. Or I have a lot more detail and go through a lot more lengthy explanations of what's going on in my book, Goodbye Quarks, the Onium Theory, which is available on Amazon. I also have 2 other books on quark theory, quantum field theory, that are also available if you want to do research on my research on that. So I appreciate you watching, and I hope you enjoyed it. Please like, share, subscribe, and I'll see you next time. Bye.